Hello, everyone. Final talk for the Data Science Analytics track. Thank you so much for staying with all of us through all of this and or streaming this later, whichever one it is that you're doing. We've got Bosco Ho talking about tweaking the rise and fall of empires and economies. Now, Bosco's bio is just full of all the words: data engineering, computational biologist, specialization, data viz, visual impact, models of the world, Python, JavaScript, graphics. So I'll let him tell you how all of that makes any sense. Please.
Hey everybody, it's been a long day and I'm glad you are sticking with us, and I think the guys are doing a fantastic job keeping all the technical pieces up and running. So before we begin, I'll go straight into it. So the talk is called Tweaking the Rise and Fall of Empires and Economies. So who am I? I'd just like to say that I spent probably the first part of my career as a computational biologist making computer simulations like the one on the screen. I used to build them, run them, study the data, and make cool little movies like that. Switched to scientific programming and full stack development at some point. So at one point I was working at an epidemiology lab in Melbourne, Melbourne Uni, and even worked with James Cook University for a while. And there I was actually tasked with, amongst other tasks, translating a MATLAB code base to Python. Now I'm working for a Bay Area company. It's an Internet of Things company, and they're doing distributed control, trying to manage industrial controllers. And I'm on the data science team there, and I'm making sort of data munging apps, visualizations. So that's my experience. And amongst all this, I just really love models, and I kept a big interest in reading about models in a big wide world, and I'm particularly interested in simple models. Models just use differential equations. I know we're in the world of big data science, but I think there's a lot of insight to be mined in small tractable models. So in this talk, I'm going to be hopefully covering some of the most interesting models I found that are quantitative and I think reveal some real insight into our world. So I'll be covering, so just want to say, the kind of models I want to look at are based on differential equations, and what it means, it's based on calculus. And just as a side note, I was just reading recently that Isaac Newton invented calculus in 1665 when he was trying to stay away from Cambridge during the Great Plague. So in that time, he invented calculus, and calculus is nothing to be afraid of. I won't be going too much into calculus. All I want to say here is calculus is the application. It's used to study the geometry of curved lines. And differential equations are just algebraic expressions of curved lines or changes of quantities. So the models we're going to look at is the very famous predator-prey model. It's called the Lockter-Volterra equation. I'm going to be looking at one epidemiological model, the most basic one. It's called the SIR model. I'm going to be looking at Steve Keen's model of economic collapse. And finally, I'm going to look at Peter Turchin's model of imperial collapse. So this talks, what I found looking at all these models is that the one thing that binds all these models together is there's this one element in every of these models: it tracks a population. And so what is great about calculus is you can write down an algebraic equation for the changes in population. And this is called the fundamental, people have called this the fundamental differential equation model for the study populations. It's simply the change of a population on the left is directly proportional to the size of the population, like our birth rate. So, our birth rate's only between 1% and 2% of the population, and that's how many kids are born every year. And this leads to this very famous, exponential growth curve. So in all the models, I'm going to talk about this equation will be buried in there somewhere, and all the other equations are just constraints on this exponential growth. Okay. So the rest of the talk will be divided in two halves. The first half will be looking at how one would go about creating a model, and it's going to be a little bit code heavy. I'm going to talk a bit about some of my personal insights on Python. And the second part, I'll actually look at these models and use this package that I've created, which I've called modeldrop.io, and you're happy to have a look at it while I'm talking, to actually bring these models to life. Okay, so before we look, to look at a particular model in detail and see the code, I'm going to pick one. And this is arguably the most celebrated population dynamics model. And it's based on this fantastic study in 1921 made by the Hudson Bay Company, which is a trading company of several hundred years old, based in Canada, Northern America. And one of the things they traded was furs of animals like lynxes. And they published this paper that looked at 100 years of data, and they found that the population of rabbits, which is in the white dots, right, oscillated over like 5-10 years, and it was followed very closely by the population of the Canadian lynx, the cat that hunts the rabbits. This data is basically the first observation that underlies all of ecology studies. And so not long after that, Lochta was a mathematician, figured out that you could model that series with this set of two equations. So these are two differential equations where the left-hand side talks about the time change of x, which is rabbits. And the other equation talks about the time changes in y, which is the lynx. And the changes in the population are related to the populations. So I won't go into this too much detail, I'll just present it. If you've had a calculus background, I think it'll be pretty obvious, but if you don't, bear with me, it's not going to be such a big problem. Okay, so what I want to show you here is how I would have programmed or implemented this differential equation, solved it as it changes over time, using a Fortran style program. What I did, I just went to the internet and went through a bunch of really great works where people have implemented a lot of Volterra equations and showing how to do it. Now, this is perfectly fine. It's the kind of code I would have written 20 years ago when I started scientific programming. But in some ways, it's not going to help me go into the next step. I'll show you what the problems are. Now, I'm looking back at this, after 10, 15 years of Python programming, and I see how I could have improved it. So one of the issues, obviously, with this kind of code is that all these variables are declared on the global scope, right? That makes it really hard to do any consistent checking. And also, the variables, you can't really reuse them in any meaningful way. Another issue I have with this kind of code is that, you're trying to calculate these differential equations and calculate them over time, and you're going to do a lot of looping. There it is, there's a main loop, and you actually have to write these equations. Now, the way they've done it here is they've actually embedded the looping, the calculations of the times, and the differential equations all into one block. What that means is you make one mistake in one place, and it's going to cause problems with all these other steps. There's really no isolation of concerns, right? Another issue I had with this kind of code, which is the kind of mistakes I used to make, is I would plot the things directly using code. And I can see from this here that's using the matplotlib library. I have a certain, I've used matplotlib a lot, and I have a certain love-hate relationship with it because I believe it's technically a fantastic package of what it can do, but the API is really terrible. When you're forced to write code like this, it makes it really, really hard to make changes. Okay, so these are just some of the issues I've had with this kind of code. I've written them in the past, and one of my side projects was, can I take some of the things I've learned in Python, create a package that would allow me to rewrite these kind of models in a much easier way. And so I've created this package called modeldrop. It's actually evolved several times, and I've tried different pieces of technology, and hopefully I'll talk about the kind of technologies that I'm going to use. So I know this is blast of code, but hopefully you'll see that this code is all that I need to do to recreate the Lotka-Volterra equations. So what I've done is I've created a base model which does all the heavy lifting, and then the rest of it you can just declare all the things you need for the solving of the equations, and then you can just let the model do all the hard work. So it's actually a very what I call a declarative style of programming. That means that when you come up and set up model, you just have to think about the constants and you just shove it into this dictionary called a parameter. That way you can collect all the things you need in one place, and you can reuse this, and I'll show you how I reuse it later. Another thing too is as you set up the equations, you go, okay, so these are the parameters I might want to use in my equation. These are the actual populations of the I want to sort of track, and I put it into a dictionary called variables. And then the differentials is the changes. I call it div, and I put it in predator. Now, in this particular case, I can actually look up the strings and check if they match or if they exist. I can do consistency checks. Okay, so I believe one thing I want to do is like allow myself to write the code in a way that's readable. And this is a bit of a subjective thing. So in the old days when I was a scientific programmer, my main aim is to reproduce what I might see in a printed equation. So this is the Lotka-Volterra equation, and this is the form that was used in the Fortran style code. And you can see that there's the minus cy, exy. Now the problem is if you read clean code and good programming practices, this kind of programming for someone who's not absolutely familiar with the math is actually really confusing. So the way I've written it using model drop, I would expand it out into this much larger term. At first blush, it looks like it's a lot more work, but you can actually see that collecting it in dictionaries, it's kind of like a type. It's actually collecting as type information. I can actually track my own mistakes as I make it. And I believe that you can actually see by meaningful variable names that they're related. Okay, so another thing I wanted to do was separate all the different steps of the calculation, initializing the variables, calculating the changes, put them in different methods. This actually helps me manage the complexity. But more importantly, once I was able to package the differential calculation into a method, I can actually repackage that into a function and then pass it to SciPy. Why that is important was that in an early incarnation of this package, I tried to do the integration myself and it wasn't good enough. My math is just not good enough. But by being able to repackage it and put it into a function and send it to SciPy, I can use SciPy, put it through NumPy, and then send it to a third-party library, which is packaged with SciPy. It's called ODE-int. It's actually a Fortran library that's actually built, that's actually incorporated in SciPy. One thing I've learned is if ODE-int can't integrate it, you probably can't integrate it because it's actually ODE-int is a 40-year-old Fortran library that's been tested to the nth degree. Right, so at this point, I've implemented my Lotka-Volterra equation. I produced a bunch of numbers. What do I do with it? I actually want to see it, and I want to play with equations. So what I found recently, I was actually tasked at work to learn how to use Dash, and I love it. What Dash does, it actually wraps JavaScript, a whole subset of React into Python, and I can write Python code and create a UI. And at the same time, I can use Plotly and generate graphs. I won't go into that very much. I think a lot of you guys have looked at it, and there's been other great talks. What I want to show you is I've actually created some scaffolding. So in my model, to actually set up a Plotly plot, all you have to do is add this little dictionary here, add some markdown, give it a title. And this is where collecting variables, all the variables together is really useful. I can just use a string and indicate what variables I want to show my plot. I don't have to think anymore. I've delegated that to the model. And then to know what kind of things I want to tweak in the model, I just have to literally list all the parameters I would like to change. Right, so I've set it all up. I pass it through an adapter. This adapter is running Dash. It's actually a Flask web server. And then, well, I'm going to live demo the software. Just before I do that, I'll show you why I did all this. Here's some data. And then here's the Dash rendered model. So there's a markdown with equations, and here is the results of the model. So in the blue, we see the populations of the predator rise. In the orange, we see the populations of the prey drop, and the prey all die, and the predator all dies. And there we've replicated in this equation the data from the Hudson Bay Company's biological study. Now, what's really great is I can now tweak things. What if the prey grow a little bit faster? Ooh, okay, so you can actually support a larger predator population. What if the predator was a little bit more efficient? Oh, it actually means if the predator's predation rate, if they hunt them a little bit faster, the actual predator population drops. Anyway, so what that means is I can now tweak the parameters here and see the results on the side. Okay, so that was the first model. I've described model drop, a way for me to sort of look at models. And now I'm going to go through some of my favorite models and show how using model drop and the Dash UI, I can actually start demonstrating very clearly some of these models that exist in the world. So I'm going to look at the what's called SIR epidemiology model, and it underlies the mathematics of how the common cold spreads, for instance. And so I'm going to go to this page, and I've got it set up here. So the SIR model is you have three populations of people. You have the susceptible, which is in blue, you start off. And then there's a small population, orange, which is infected with the cold. And green is people who've got the cold and they're recovered, and then they won't get sick anymore. And so this very simple model is a sort of a basic model in all epidemiology textbooks. It underlies COVID. It underlies, I was working in tuberculosis lab and HIV. So it's the same math that most epidemiologists use to model how a disease progresses. Now, in this model, you have to add in what's called the reproduction number, and you got to set it in by hand. So I've got to set it 3. It means everyone who gets sick will eventually infect 3 people. And as you can see, if you bump up the reproduction number, the dynamics of the population, who gets sick and when they recover, completely change. And when we talk about in the COVID literature trying to get R to 1, or less than 1, so when it happens, when you drop it less than 1, you can see that infections literally drop and the disease disperses, and that's what they mean when R is less than 1. Okay, so just going to run through that very quickly. So the next model I want to look at is economic modeling. So in 2008, we had the GFC, the global financial crisis. Apparently, mainstream economists said no one could see this coming, quoted by Robert Rubin, the former US Treasury Secretary. But in fact, late in 2009, the Dutch academic actually went through the literature and said there were actually 11 academics who did predict the global financial crisis. And they actually published and had reasoning. And out of them, one of them even had a dynamic population model, just the kind of models that I like to look at. This guy's named Steve Keen. I've been following his work for years. He's got a Patreon account. He's actually retired from academia and survives on Patreon. He's building beautiful models of the economy, including using energy. So it was a real dream of mine to be able to build and play around with this model. And I finally did it after making model drop. So in his model, let me see. So in his model, you have basically 3 bunches of people. You have workers in blue, you have capitalists in orange, and you have bankers in green. And he's got a very simple model using elegant dynamical restatements of macroeconomic identities and some psychological insights. And in this graph, what we have here is the share of the GDP over time. And in this model, he can reproduce what's the classic business cycle, profits drop. Let me see if I can expand this out a little bit. So the idea is over time, wages get, more workers get employed, they get more money, but then the capitalists lose money, and then they invest less, and then they employ less people, and you get a business sort of oscillation, classic business cycle. And at the same time, as the bankers, as things improve, the capitalists would like to borrow money from bankers. So the banking debt actually goes up, and the bankers' income comes from interest payments from the massive debt. So that's all, nothing particularly special. So I'm just going to set the depreciation rate. So if I was to do it like this and I expand it over time, it always stabilizes. But what Steve Keen found was if you adjust the depreciation rate, which is capital is the amount of machinery and the capitalists have, if you can actually expand its depreciation rate, then you get this incredible oscillation where the system breaks down. So depreciation is basically your machinery actually gets old and it has to be replaced. So capitalists always have to be borrowing more money to replace the machines. And so in 1995, Steve Keen actually observed something which is, I think he's the only person who sort of stated it, that in a dynamic model of the economy, you get this effect where you have business cycles and it actually moderates, and you have a quiet period, and at some point the whole thing oscillates and then it causes a crash. And the whole reason is, I'm just going to skip down, I don't have a lot of time left, is that debt balloons out and it causes the oscillation. Okay, so I'm going to skip to my very last model, and this is the model by a polymath by Peter Turchin. 20 years ago, he was probably the world's foremost population ecologist, theoretical population ecologist. He wrote really fantastic textbooks on it, and then he got bored. He goes, bored with population ecology. So what he decided to do was switch and apply these same methods to the study of the end of empires or imperial collapse. And he started studying the Roman Empire, Chinese dynasties, and he found there were certain models that he could use to understand its behavior. And based on that, he decided to apply it to the United States. And he came out with a great paper in 2012 where he integrated a whole bunch of sociological studies and historical studies to study the patterns of domestic violence in the United States. And this is the graph I took from his paper. I believe this is one of the most interesting data science graphs I've ever seen. And here it is. And he did basically, all these regressions, Fourier transforms, but I can just summarize what he found, and I hope you can see this. I think it's pretty clear. There were 2 cycles of violence. One is a 50-year cycle between 1860, 1920, 1970, and the other one is a 120-year cycle. And in that paper, he actually made a bold prediction in 2012 that 2020 will be the next peak of violence. What I wanted to do was study the model that Peter Turchin made to understand this particular red curve, which is the 120-year cycle. And I finally did it with model drop. I actually had robust and Python package, and I implemented it. And here it is, the Turchin elite demographic model. It's a very simple model. It's got 3 elements. In the blue, you have a bunch of producers that make all the food. And orange, you have a bunch of elites who take a big chunk of the food. And then what happens is with the elite, if they don't have enough food, they will start fighting amongst themselves. And in the green, you have a state which improves the productivity capacity of the whole system or the state. And it will also keep the elites from infighting. And so he made this model and showed it is natural, in a lot of these parameters, you have this rise and fall of the state, and you have elites growing, and then they all fight, and then they all die off again. And then it starts off a quiet period. So this model was the basis of the elite model. And he had 2 really interesting observations. One is, I'm going to come to this graph, which is green is the total production of this state. It actually rises up here, and then it all crashes down. But what happens is the producer, they actually get less share of the food because elites take it. And there's a crossing point where the elites take more than half the food. This is actually emblematic of our society as well. But but what it means is, even though the total production improves, the share of it is unevenly distributed. And the most surprising thing is, if you actually divide by population, the earnings, the amount of food that an elites get per person, there's only a glory period, a very short time, and throughout most of the period, the elites in general are actually getting worse. They're actually getting poorer until the actual bottom of the cycle. So even though here you think the elites are getting richer, here actually in this part, the elites are actually getting poorer. And the whole idea is when they're getting poorer, they get upset. There's a whole population of upset or overproduction of elites, and they will destabilize the political system. Okay, I'm coming towards the end. I'm going to be cut off soon. So I'm just going to wrap up here. Just one of the final words. Just want to say, sometimes we look at our own particular models and we get a bit of a tunnel vision and we just look around what we're doing. I think there's a lot of value in trying to sort of jump out and look at a couple of other different models, other systems, and tie it all together. So with me, I've looked at dynamic population models. I think they're fantastic. I think there's a lot more of them, and I think there's a lot of value to be studied in them. And I just want to say I built this package, which I'm really proud of, and it's really helped me look at these models, and hopefully it helps you. The final point I want to make is, hopefully you'll realize that tweaking or being able to make these models and make changes really instantaneously will help bring insight into what is actually going on. So with that, thank you. Whoops.
Thank you, Bosco. That was really excellent. And I'm just gonna have to watch this a couple more times. This talk kind of did exactly what I expected it to do, and that was very interesting. I don't know that we've quite got time for questions, so I'll let everybody ask them in venue list for you later.
Okay.
And thank you. Thank you so much, Bosco. It's, yeah, it's a fascinating little romp through a whole heap of different things.